Well, thank you very much, Roger. Thank you also, Donna, for this very nice introduction. You know, I have only to talk about applications. About the film, you know, the people at the Stockholm said that they were judging only science. Okay, they were not in the Oscar business. Okay. So anyway, I think Donna, it's always a difficult time to follow Donna, you know, because she's so good at presenting things, and so I'm going to use that too. So anyway, the title of my presentation is really a passion for extreme light. And this is very easy to understand it. You know, when we did CPA, we started to do CPA, and, you know, it was a wonderful concept. We could really amplify. The first demonstration was at a millijoule level. And then, you know, we could really push it to the joule and 100 joules. And every time the concept seemed to work, you know. So this was always very intriguing to see how far we could go, and that comes back to one of the questions that Donna got. So anyway, what is very exciting, of course, are the applications. Okay, it's one thing to produce very, very high intensities, but the applications which follows are really mind-boggling. So I'm going to start. Doesn't work? Oh, okay. Well, no, it went too fast. Went too fast. Yeah. So, like Donna said, you know, everything started, you know, with this man, Ted Neyman, okay? May 16, 1960 was the first shot, laser shot. Anyway, and, you know, there's one thing which is really mind-boggling about lasers is the fact that, you know, you can use light, you know, to slow down atoms, and you can slow down atoms to very, very, you know, small kinetic energy, microelectron volt, nanoelectron volt, these kind of things. And that, of course, led to the development of this beautiful field of quantum optics and cold atoms and so on. But also what you can do, and this is really, you can do just the opposite. Instead of slowing down atoms, you can accelerate, you know, particles. And you can accelerate particles to very, very close to C, with very, very large Lorentz factors. And that is really remarkable. And now we can really accelerate particles to the GeV with no doubt one day we are going to go to the TeV. So you can see that with one EV atoms, photons, I'm sorry, from the lasers, you can really go through about 20 orders of magnitude from the nano EV to the TeV, okay? This is remarkable, and that, of course, you know, always fascinated me. And you know, there is a lot of, as you will see, there's a lot of room, you know, above. So this is, of course, Cherpent's amplification. I'm not going to describe it. Donna did it very well. But what we can do now, we can produce power, peak power, of course, peak power, you know, which is expressed in petawatt. Petawatt is 1,000 times, okay, the global grid power, okay? So it's phenomenal. Of course, we do that only in few femtoseconds and not, you know, CW. So we're cheating a little bit. But now, what is important also, if you can focus this power over the wavelength of light, you can produce enormous intensities, which is associated to enormous pressures. And the pressures, you know, attend to the 23 watt per square centimeters. Is of the order of 10 million times the Eiffel Tower on the top of your fingers. So this is really significant, of course. So, but there is more than this. because producing this extreme light, that's what we call extreme light, it can also produce this largest temperature, this largest pressure, this largest acceleration, this largest field, and the laser becomes, in fact, a universal source of high-energy particles and radiations. And so this is exactly what we show here. If you are focusing this petawatt laser over a small spot size, then you are getting, electrons at, not at a TeV yet, but we will come, protons, gamma rays, high field. I mean, all kind of radiations and particles, could be created. So this is extremely exciting, and what is exciting is the fact that, lasers, until CPA, I will say, was basically dealing only with atomic physics, EV physics, okay? And now, of course, with this possibility to increase the peak power to the enormous value, you can go to we can go to the subatomic regime, and that is very exciting, okay? So you can really go now in GeV and TeV and so on. This is, here I'm describing, where is my pointers? Oh, okay, let's see. Yeah, it's working. Okay, so now the focus intensities that we can really produce as a function of years, is, if I'm looking at this ordinate here, at the beginning, when the Mayman came up with the laser, I mean, we were at 10 to the 8 watt per square centimeters, and then some technique like mode locking, switching were developed, and we could go, and, we basically go 10 to the 14, and that was really the plateau. And the reason why we were reaching the plateau is because we were breaking down, of course, the materials now, and chirp pulse amplification came about, and boom, immediately, the intensity took off, okay? And now we are at incredible intensities in a regime of 10 to the 23, 10 to the 24, and soon we will have the 10 to the 25 and maybe higher. And of course, as we are doing that, we are going into new different regimes in physics. The first one is not terribly exciting, but very, very important, for applications. It is the fact that we can use these lasers, to micro machine with high precision, and because machining with femtosecond laser, of course, the heat doesn't have the time to take off. So you remove only, a very, very precise amount of materials without basically any collateral damage. So this is good. And this is what's nice also, you can use that on a piece of metal, but you can do that also on the eyes, okay? And this is the CPA, in fact, revolutionized ophthalmology, because every year, I think you have 1 or 2 million patients, or eyes, which are having these procedures. So it's a very, very, it's been very important for society. And so you can see that the lasers, can be focused, say, in your cornea here, and we can really take some very, very thin slip of materials, slide of materials here, and you can, this way, you can correct the visions, myopia, hyperopia, and astigmatisms, and so on. I'm not going to go very much here. For example, if you are really doing this thing with 50 picosecond pulses, 50 picosecond, after all, is kind of short, But, this is, you don't get into the cornea something very clean. If you are using 300 femtosecond, it's very, very very, very clean. Anyway, so I'm not going to, now we are going to go into more in physicsy things. As I said, you know, after 1985, the intensity took off, and we were crossing new regime. And the first regime, of course, that we crossed was this relativistic regime, the regime where really the electrons around the nucleus now could reach the speed of light, change its mass, and so on. So, and the optics, of course, regime completely changed, okay, because of that. And one of the very important applications, you will see, is going to be in producing very high energy particles, in electrons first, and then in protons. So electrons, in order to produce particles, to accelerate particles with the laser, what you do is something which was introduced by Toshida Tajima and Dawson in 1979. But of course, they had to wait for the laser, for the CPA to be able to use it. And the technique doesn't respond. Yeah. So the technique, in fact, is very simple. Okay. You take your laser pulse and you whack it into this plasma, a supersonic gas jet, and you are going to ionize the plasma. And you are also going to generate a plasma wave, very strong plasma wave, which is going to basically propagate at the speed of light. And the electrons, are going to go, like when you do surf, the electrons are going to be trapped, or some of the electrons are going to be trapped into the trough or into the plasma wave and be dragged at the speed of light. And what is absolutely amazing is the fact that because it's a plasma, you don't have to worry about damage threshold. This is the thing which is limiting conventional acceleration techniques. You can really put a lot of, you can have very large intensity to deal with. And so you can produce very high energy beams. And typically, the energy beams that you can produce is in GeV per centimeters. Okay, for some people who don't really know what the GeV is, well, if you want to try to produce, if you want to try to produce GeV beams, okay, you need this kind of facilities. Here, for example, at Synchrotron Soleil, 3 GeV, I mean, enormous facility. And you see that what we do is we can produce that over centimeters. Now, it's typically GeV. We are at 4 GeV, but it's only the 4 GeV can hold in my palm, in my hand. So now, if I'm looking at, for instance, LHC, there's a lot of people high energy physics, I guess. So this is a TeV machines, and because they are using, of course, a conventional technology. It's 27 kilometers, okay, because you can only produce MeV per centimeters. But if you were using that's microwave, we are using microwave cavity. Now, if you are using, of course, laser wake field acceleration, I mean, in practice, the system will really be of the order of a few hundred meters in length. So enormous, of course, improvement. And so now, but you can do even better. We know that we could do even much better, in fact, and we could do very, very much better if we were, and this is what we are trying to do now, instead of using visible short pulse laser, you see, you have this pulse which is about 20 femtosecond here, and you have about the period is about 2.5 femtoseconds. So you have something like 10 to 20 cycle in your pulse. Okay, now what we are trying to do, I'm not going to describe it, I don't have the time, but what we want to do is really to produce single attosecond pulse, okay? And with efficiency, here you have several joules, and we like to have also a joule or fraction of a joule maybe at this, because this pulse is attosecond, is per definition, you know, just Fourier will tell you this, is that you are in the X-ray regime. And so now the idea is that we are pursuing with Toshitajima now is to go into this X-ray regime and trying to do wake field acceleration because you are in the X-ray regime. Now you can do it in solid. With solid, you have, of course, you know, you are 10 to the 23, 10 to the 24 electron per cubic centimeters, 6th order of magnitude above what we were using when we were using gas. So you should be able really to produce TeV per centimeters. Okay, this is phenomenal, and to think that you know you could have something like CERN, you know, on a finger. Okay, this is a little bit provocative, but it's coming. Okay. Now, we talk about electrons. We have to talk also about maybe protons. Proton also, we can do that very well, okay? And in fact, we should be able really to produce GeV protons relatively easily and simple, okay? Here you have, for instance, a very thin target, you know, nanometers in thicknesses, and you whack again the laser, you know, high intensity lasers into this target, and then you can get really proton accelerations. And now we have the records about something like 100 MeVs, 150 MeVs, but by using a technology I just showed you, which in fact is really relying on single cycle generation, like I showed you, we should really be, we should produce this GeV very easily and very efficiently. And of course, this is the competitions, of course, is here. Here you have what is a GeV proton acceleration or something like that. So you see the immense simplifications, compactification that we are getting with the laser. And of course, this is what gets us excited. So let's see, next one. Yeah, so of course, let's talk about application now. Of course, the fact that we can produce now, you know, particles in MEV, GeV regime very easily. I mean, and in particular, we could really do something like proton therapy. You know, proton therapy is really the therapy of choice, okay? Because we don't, you know, when you have a tumor, you know, located, you know, maybe in your brain or something. I mean, before to burn the tumor, you also burn, you know, the tissues in front of the tumor, okay? But this is not exactly the same. This is not happening, or it's less happening with protons, because the protons are going really to be absorbed, you know, at the Bragg peak, okay? And mainly, and you can adjust this Bragg peak as a function of the energy of the protons. So this is very exciting. And we can do also some nuclear therapy, nuclear diagnostics, and so on. You know, very, very nice applications, you know, of CPA, nuclear medicine and pharmacology, and so on. Now, there is, of course, something very, very important. And this is, you know, I relate these problems of nuclear waste, you know, with what the motto of Alfred Nobel for the greatest benefits to humankind. And this is the type of things we would like to do, is really to trying to see if we can use these protons that we are producing to produce neutrons. And then when you produce neutrons, you can do transmutations. And, I mean, here we have, because, nuclear energy, is very good. You have only, if you could really solve this problem of nuclear waste, it would be almost ideal. So this is what really I would like to spend the rest of my life trying to do. And so here, for instance, we have, the troublemakers really are these minor actinides. And like neptunium, for instance, half-life of 2 million years. Okay, but if you come with neutrons, which has an MeV's energy, then you can fission this nucleus, and then you can obtain 2 smaller nucleus. But now, the lifetime of this nucleus are measured in minutes, or in hours, maybe a day, okay? But very short, of course. You go from 2 million years to minutes, it's very short. And then even they can decay to a stable form, okay? And this is really something that is really appealing, because we could produce these neutrons with the necessary energy, and even with compact systems, and we could even go, to nuclear sites to solve the problems. You could move that around, and because it's compact, could maybe 18-wheeler could do it. So this is the end of my talk, and I'd like to conclude, that extreme light is capable of generating the largest field, the largest acceleration, the largest temperature, and the largest pressure. Of course, I just show you a snippet of all the applications here. It's an enormously active field, with thousands now of people working on it. And I conclude that it carries the best hope and opportunities for the future of science and technology. But just coming back to the question which was asked to Donna, how far could we go? Well, I think we could go very, very high. We are far from reaching the limit, and I'm convinced that the best is yet to come. Thank you very much.
Questions?
No. I guess I was very clear.
How can you use
I don't see you.
TV? I'm here on your whatever it is.
Okay.
We know that LHC and CERN is very large, very expensive. You can produce the same amount of energy, or can you do similar experiments and get similar results to the ones that they can get?
Yeah, that's a plan. That's a plan. Of course, because it turns out that, of course, it's not just a question of energy, as you say. It's a question also of beam quality and brightness and so on. Okay. It turns out that we are there in terms of brightness. The beam are quite nice. There's a hurdle that we need to work on, and the one which is, of course, I would say maybe the most formidable hurdle is the rep rate. Of course, here, yes, we can really produce this giant pulse, TeV giant pulse, in 10 to the 23 or so watt per square centimeter and so on. But the rep rate is still very weak. okay? The reason why the rep rate is weak is because the material doesn't have the time to cool, okay? Usually, we are talking about glass, or we are talking about sapphire. They are not really very good conductor, except that in case of sapphire, if you cryogenically cool. But there is these problems of trying to now, after we get the high peak power to produce the electrons, to produce the repetition rate, okay? So 10,000 hertz, repetition rate, people are used to, and things like that. But we are getting there. We know how to solve this problem. This problem is an engineering problem. We know how to solve it, and so then we'll be back to the same type of, we will be able really to reach the same performances that LHC also.
Yeah, much cheaper, right?
And yes, much cheaper, and more compact. Because, as you know, unfortunately, because now you cannot do otherwise, I mean, the next one is 100 kilometers.
Yep.
So the civil engineering, problem of a program like that are enormous. So it should be much more compact, yes.
We have a question.
Oh, okay. So do you think that your high-energy laser device can be used to further examine if the electromagnetic fields can distort the space or the space-time structure?
Oh, absolutely. Absolutely. This is something I didn't have the time to evoke. But of course, we like really, the idea, we like really to of course, break down the vacuums, boil down the vacuum, these kind of things. And we should be able really to go above the Schwinger field. Particularly with the technique I showed you, where we are using X-rays. So far, we have been using visible light, to produce these high intensities. Now, the push, is we would like to use X-rays. And with X-rays, of course, you will be able, in principle, to focus the beam smaller, but also you are going to have a shorter, and you can get higher field, because you are, in a regime where the ponderomotive force, is very high, because you have a single cycle. I don't have the time to but this will be enormous advantages. So very quickly, we should really go above the Schwinger limit, Schwinger field. It's not a limit.
Okay. Do you think that if you use the gamma ray, it will be better than the X-ray?
Yeah, well, I mean, you have to produce it.
Do you want to try it?
Of course, but I mean, you already. I'm very pleased if we go to the X-rays, okay? Because squeezing 1 joule into X-rays, I mean, Roger will be delighted. I mean, people, basically what we are talking about is something which is a free electron. I mean, it's something which is in competition with the free electron lasers, but of course more compact and so on. Okay, where we could really squeeze coherent pulses, in high energy coherent pulses in a attosecond regime, in a KeV. Yeah.
Okay, thank you.
Thank you for the amazing talk, very smooth. And I'm wondering, so when you were studying the extreme light, what are some difficulties or troubles that you face that you want to share?
Oh, many difficulties. No, it's we have, of course, this what I showed, is very challenging. For instance, this trying to get this single cycle in the X-ray regime. I mean, we have a path, which is very visible, so we can do simulations and so on. But of course, the devil is in the details, all that, and we have to do the experiment to prove it, like we did with Dana way back when. It was also a very, very, very challenging proposition, right, Dana?
Maybe a final question.
Hi, very nice talk. I've got a kind of a applied question. You say that you can use these lasers to do nuclear transmutation.
Yeah.
What sort of infrastructure challenges would be in trying to apply this to every nuclear waste site in the world, or you know, how much money would have to be invested to allow these beams to be available for all these nuclear sites?
Well, I mean, right now, you know, it takes, I mean, we could, you know, we could really build, for instance, the idea will be to build one facility for transmutation per 7, you know, reactors. But the nice thing about it, I was mentioning it, is it's relatively compact. I mean, it should be compact. So we could really move this facility around, okay? And so that's something, because, you know, people don't want to move the nuclear waste, okay? They don't like, nobody likes that. And, but if you move the lasers, you know, it's much better.
Thank you very much.
Gerard, thank you very much.